right, so section 20 is on the derivatives of exponential functions. So it says, look at a graph of f of x equals e to the x. This is a very special graph. So if you try to find the slope at various points, you can see that the slope is not very steep. It gets steeper, it gets steeper, it gets steeper, and so on. The slope is never equal to 0, although it does get pretty close to 0 over here, right? Okay, if you graph all of the slopes, if you're like, oh, my slope was like 1/4, and then it was like 1/2, and then it was 1, and then the slope was 3/4, and so on, what actually happens is the derivative of e to the x, so the slopes of e to the x, make e to the x, okay? So the derivative of e to the x, it's the easiest one in calculus. It's e to the x. It's itself. Okay, it's well, I wouldn't say the only thing that has a derivative of itself, because 0 has a derivative of 0, right? There might be other things, but yeah, so the derivative of the natural exponential function is e to the x. So e to the x, its derivative is e to the x. Easy enough? That's why you guys have that little cartoon on your due dates page. All right, so it says differentiate the function. So this means that I still have to use rules. Like, I still have to consider like things like the chain rule, right? This is just our general form. So if I have e raised to just x, its derivative is e to the x. But if I have something like e to the 5x plus 3, then its derivative is going to be itself e to the 5x plus 3. And then what do I need to remember? Times, what do you think? 5, right? Because of the chain rule. This is in the form e to the w, so its derivative is e to the w derivative of w, right? Still doing that chain rule. So in this first example, its derivative is going to be e to the 5x plus 2 times 5. Did I do exactly the same problem? Close enough, huh? I do that all the time where I like think of the same thing. All right, so it's going to be 5 e to the 5x plus 2 is how we'd write that. All right, so think about the next one. It's e to the w is its form, so its derivative is e to the w, so e to the sine of x times the derivative of w. So the derivative of the power, cosine of x, exactly. So it's like cosine of x times e to the sine of x. Now, I don't care if you write it the top way or the bottom way, it doesn't matter. You could put parentheses here if you want, doesn't matter. All right, so how about this next one? So f prime of x is going to be e to the square root of x, but then we need to take the derivative of the square root of x. So at this point, you guys are probably still rewriting the square root of x as x to the 1/2, and then taking the derivative of it. Are you guys doing that? So its derivative is going to be 1/2 x to the negative 1/2. I want you to get to the point where you have the square root of x and you know immediately that its derivative is 1 over 2 root x. Okay, that's a good one to just know because we see it all the time. Do you see why it's 1 over 2 root x? Because the square root of x goes on the bottom because it's a negative power. So putting this all together, so I have e root x times 1 over 2 root x. I end up getting e to the root x over 2 root x. And that's your answer. All right, the next one, g prime of x. What do you think we use here? Your fave, quotient rule, right? Low d high minus high d low, all over the square of what's below. So I do low is 1 plus x. D high is e to the x, right? The derivative of e to the x is itself. Minus high is e to the x. D low, what's d low? 1, all over the square of what's below, 1 plus x squared. So the nice thing about these e to the x functions is if you have the product rule or the quotient rule, you're going to have like something in common. See how we have the e to the x in common on top? So we can pull it to the front. And usually there's some simplifying that can happen. So we have an e to the x in common. So we just factor that to the front. And then we still have that denominator of 1 plus x squared. So do you see how it ends up being x e to the x over 1 plus x squared? That's our answer. All right, so the next one. So I could do e to the natural log of cosine of x times, well, I don't know the derivative of natural log, though. Do you see any shortcuts? Yeah, this ends up just being cosine of x, right? So don't overcomplicate things. If there's a way to simplify, especially like when we get to the logarithms, like the derivative of a logarithm, there's going to be lots of ways to simplify. But in this case, we know that when we have e to the natural log, that's going to cancel, right? So this went away. It just became cosine of x. So that means its derivative then is negative sine of x. Done. All right, so how about this next part? So I do e to the 5x times 5 from the chain. Do you guys get this? Minus 4 times e to the x plus cosine of x. So if you wanted to clean it up a little bit, I would just write that as 5e to the 5x. And then really there's nothing else that you can do. Okay, so why didn't I do like the product rule for that 4e to the x part? Why didn't I do the product rule here? As I'll see. Do you remember that rule? So if it's just a constant, you don't have to do the product rule because the second part of the product rule will be 0, right? You guys are sleepy this morning. Goodness gracious. All right, so this next one. So I'm going to have 1 plus 3e to the 2x, and it's raised to the 1/2. Okay, so go ahead and try along with me. Try to write the derivative. See if you get it. So I get 1/2, 1 plus 3e to the 2x to the negative 1/2, right? Because it was in the form w to the 1/2 originally. We all see that. And its derivative is 1/2 w to the negative 1/2. So we have that part, 1/2. The w stays the same to the negative 1/2. And then we multiply by the chain. So our chain is the derivative of the inside. Yep, 3e to the 2x times 2. Did you guys all have that? And then you can simplify a little bit, like the 2 and the negative, or the 2 and the 1/2 go away, right? So that negative exponent is now on the bottom as 1 plus 3e to the 2x under a square root. And then I have 3e to the 2x on top. So that's how I would simplify that. Are we ready for a double chain? You guys hate the double chains. All right, so we're going to have, this is sine of e to the cosine of t, and it's squared. Okay, so we're just looking at the whole thing. What is happening to this whole thing? It's something squared, right? So we're starting with that. Yeah, so we're going to have 2w. That's how we started out. So sometimes I just write parentheses, and I'm like, well, what was w? W was the sine of e to the cosine of t. And then we multiply by the derivative of w. So if you think about this as being a new problem, sometimes that helps. Our w was sine of e to the cosine of t. So our question is, how do I find the derivative of that? So the derivative of sine of e to the cosine of t, well, that's in the form sine of w, right? So if I'm taking the derivative of something in the form sine of w, it's going to be cosine of w, right? So I'm going to have cosine of whatever w is. So w is still e to the cosine of t in this case. But then we need times the derivative of that w. So what's our very last part? E to the cosine of t times negative sine of t. Did that make you sweat a little bit? Oh man, it's rough. All right, and that's all together, the entire answer. All right, so the question is, well, we know the derivative of e to the x, but what about the derivative of a to the x? Okay, so if you think about e to the x, you know, it definitely has this shape like this, but that's not our only exponential function. So e is a number like 2.718 something, right? So e to the x has a certain like steepness. But if I had something like 8 to the x, it would be even more steep, right? So we need to figure out how that's adjusted. And the way that it's adjusted is by tacking on the natural log of that number. So if I had like 8 to the x, its derivative is 8 to the x natural log of 8. Does that work for e to the x? If I said its derivative is e to the x natural log of e? Yeah, because natural log of e is just 1, right? So it still works for e to the x. So you could just know one formula and just always memorize that. So this is one that you definitely need to know. So in this case, I have 2 to the something. So this is in the form 2 to the w, which has derivative 2 to the w times natural log of 2. Okay, so we're going to use that. So for g prime of x, I'm going to have 2 to the 3x plus 1 times natural log of 2. And then times, since this wasn't just a plain x, it was something other than x, I need that derivative of that w. Yeah, times 3. Does that make sense to you guys? All right, so think about number 2. It's a little tricky. Okay, if you got this one, you're definitely doing well. So it's going to be 2 to the 3 to the x. So it's not 3x. Do you see it? It's 3 to the x. Times natural log of 2. Yeah. Times the derivative of 3 to the x. Ooh, the derivative of 3 to the x. 3 to the x times natural log of 3, right? Do you get it? All right, so how about the next one? So y prime, so this is 10 to something, 10 to the w, and the derivative of 10 to the w is going to be 10 to the w, natural log of 10, and then times the derivative of w, right? So we're going to do 10 to the tangent of x times natural log of 10, running out of room, times the derivative of that power. So do you guys remember the derivative of tangent? Secant squared, yep. Does that make sense? Okay. All right, so find the absolute maximum value of the function f of x equals x times e to the negative x. Okay, so in order to find a maximum or a minimum, so if you think about a curve, the maximums and minimums occur where the slope is equal to 0, right? Or if you had like an absolute value function or something like that, or at a corner or cusp where the slope is undefined, right? So we need to figure out where the slope is equal to 0 or the slope is undefined in order to identify places where it could be a maximum or minimum, okay? So we're going to take the derivative of this x e to the negative x. So do you guys see what we need to do here? We need product rule. We also need chain rule. Why do I need a chain rule? Because that negative x is not, it's not just positive x, right? So I'm going to do first is x times the derivative of e to the negative x. So I'm breaking it apart like this. So the derivative of e to the negative x is e to the negative x times negative 1, or negative e to the negative x, plus the derivative of x is 1, and then times e to the negative x as it is. So I told you with these exponential functions, a lot of times you're going to have like a repeated factor that you can pull to the front, right? So do you guys see how you have an e to the negative x in common? We're going to pull that all the way to the front. So we're going to have e to the negative x times negative x plus 1. See where I got the negative x times negative 1. And I want to find when that's equal to 0 or when it's undefined. So this is 1 over e to the x times 1 minus x, right? How about the 1 over e to the x? Is that ever making it equal to 0? No, because I have a 1 on the numerator, right? There's no way to have a fraction equaling 0 unless the numerator is equal to 0. So it could get really close to 0. If I make x like 10 trillion, 1 over e to the 10 trillion is really close to 0, but it's not 0, right? So you have what? 1. That's it. 1 is the only one. So what we're going to do eventually as we start talking about maximums and minimums is this is a possibility. It doesn't necessarily have to be a maximum or minimum. Think about x cubed. X cubed tapers off to a slope of 0, but it's not a maximum or minimum. Does that make sense? So just because it's equal to 0, it doesn't mean it's a max or a min. So in order to find it, we would have to check the slopes before and after it. We'd have to say, well, in order for it to be a maximum, you would have to go up before it and then down after it. Does that make sense? Like increasing and then decreasing. So we often do this little chart, which is kind of frustrating because the AP Calculus test never grades this chart. So you have to like explain what's in the little chart, but we'll talk about that a lot throughout the year. And we plug in numbers on the left and the right side of it into the derivative because we want to know if the derivative is positive or if it's negative. In other words, if f prime is positive, it means that f is increasing. It's going upwards. The slope was positive. So if I plug in like 0 into here, I get 1 over e to the 0 times 1 minus 0. What's e to the 0? 1. So I have 1 over 1 times 1. That's a positive number, right? That's all I worry about, if it's positive or negative. So that means f prime is positive when I'm on the left side of 1, which means f is going upwards. And then if I plug in 2, I get 1 over e squared, 1 minus 2. Well, 1 over e squared is positive, but what about the 1 minus 2 part? That's negative. So I have a positive number times a negative number, which is negative. You guys kind of did stuff like this in Algebra 2 and pre-calc. Do you guys remember like critical values? That's why you do this. It leads to this. So can we say that that's a maximum then? Yeah, because I went up, and then I got a slope of 0, and then I went down, right? So what's happening on the graph is it looks something like this. I had a positive slope, I tapered off to a slope of 0, and then I went down. That's a maximum. So then we would be good. So we would say there's a maximum at x equals 1, but I asked for the absolute maximum value. So I want to know, well, how high does it go? How do I find how high it goes? Go back into the original, right? So we're going to find f of 1. So I have 1 times e to the negative 1, which is 1 over e. So we're going to say absolute max of 1 over e located at an x value of 1. So at x equals 1. You guys read my 1 over e, it's a little sloppy. 1 over e. Yeah. I did, because I wasn't really worried about that because it's not making it equal to 0. Yeah, and you could try to solve it. Like you could say e to the negative x equals 0 and try to do like natural log of both sides. But do you see how you'd get natural log of 0? So it wouldn't work. There's no way to have a 1 over something ever equaling 0 because you need a 0 in the numerator. Yeah, does it make sense? Okay, so one last step on this. For the AP test, like I just told you, they would never grade that little sign chart. So you'd always have to say like f prime of x is greater than 1 when x is less than 1. And you'd say like f prime of x is less than, sorry, not 1. Sorry, f prime of x is greater than 0. It's positive, right? So f prime of x is greater than 0 when x is less than 1. And f prime of x is less than 0 when x is greater than 1. So you'd need to say something like that in there. All right, implicit differentiation. So you guys try these ones, so practice. So try A and B, and we'll talk about them. Okay, so check your steps, make sure you have the same thing. So this first one would involve the product rule, right? So we have an x term, and then we have times e to the y. We know how to take each derivative individually, but together, they would need that product rule, right? So we're going to do first is x times derivative of the second is e to the y times dy over dx because it's a y term. Plus derivative of the first is just derivative of x is 1 times the second normal is just e to the y. So I don't need a dy over dx on that part because I wasn't taking the derivative of the y term there. I was just writing it as it was. So that's the product rule for the first part. Minus the derivative of 5x is 5. The derivative of 2y is 2, but since it's a y term, we do dy over dx equals 0. So then we get all of our dy over dx's on one side. So I have like x e to the y dy over dx plus 2 dy over dx. And I get anything that doesn't have a dy over dx over on the other side. So I'm going to add the 5 over, and I'm going to add or subtract the e to the y over. So I'm going to have 5 minus e to the y on the right-hand side. I then pull out the dy over dx. So I have x times e to the y plus 2 equals 5 minus e to the y. So your final answer should be dy over dx equals 5 minus e to the y over x e to the y plus 2. And that's it. Did you guys get it? Good. Now remember, you might have like multiplied by -1 over -1. Yours might look pretty much the same, but you might have like -5 plus e to the y over negative x e to the y minus 2. Okay, yeah.
For like the first step, why don't you multiply dy over dx? Like, why isn't that an exponent? Since y is an exponent.
It doesn't ever go as an exponent with the y. So she's saying, why do you not do e to the y and then dy over dx up here? It's always just times, like you take your derivative of the e to the y, which is itself, and then you tack on the same level the derivative of that power. Yeah, kind of weird. All right, so B. Okay, so now we have a 5 to the 2y. Okay, so that's in the form like 5 to the w. Do you guys remember what the derivative of 5 to the w is? 5 to the w. Natural log of 5, right? And then times whatever the derivative of w is. Okay, so we're going to use that. So we're going to have 5 to the 2y times natural log of 5 times the derivative of whatever the power was. So the derivative of 2y, 2, but it's a y term. Yep, so you need dy over dx. Good. Tricky one. Do we all see that? Sean, you good there? You get it? Okay, and then I have minus the derivative of e to the x is just e to the x. And then the derivative of 7 plus y is 0 plus dy over dx, right? That's where a lot of people write 7 plus dy over dx. Did anybody do that? I see lots of errors like that. All right, so we want to get all the dy over dx's on one side, anything that doesn't have a dy over dx on the other side. So I'm going to get the e to the x on the right side, and I'm going to have 5 raised to the 2y times natural log of 5 times 2 dy over dx, and then minus 1 of the dy over dx's. So I pull the dy over dx out, and then I'm going to divide that part that was inside parentheses over. Can we do this all in one step? So it's going to look like e to the x divided by the part that would be in parentheses would be 5 to the 2y times natural log of 5 times 2 minus 1. Okay. Now, I told you that the AP writers are jerks. I didn't really say it that way, but they're not nice people. And they do weird things. Okay, so the graders are not very nice either. They're mathematicians. Mathematicians, in general, not nice people. I like to think I'm a nice person. I don't know. It's a rarity. Mathematicians are not always nice. All right, so anyway, so we have this. And they're not always going to write it like that. So they might write the answer as e to the x over 25 to the y times natural log of 25 minus 1. Why are they able to do that? Multiply, what do you mean? So let's look here first. If I had 2 times natural log of 5, if I write it that way, you guys will immediately know. Yeah, you bring the power up, right? So that's natural log of 25. Did we see that? What about this part? If I have 5 to the 2y, we're going to write it as this, 5 squared to the y. You see it? 25 to the y. Does that make sense? We would multiply our exponents. 2 times y creates 5 to the 2y. Does this make sense? So you might see that.
But wouldn't that have to equal, wouldn't that be like 5 squared plus 5y?
5 squared plus 5y. Nope, because then you would
5y?
add. If it was 5 squared times 5y,
I mean, like when you split up by the
then you would add the exponents. Yeah, so this is, remember how you multiply exponents? That's how you get the 2y. Kind of tricky. You see it?
I mean, like when you split it up, they don't like.
You can't really split it up. It would be like 5 squared times itself, y times is how you would break that apart. So it'd be like 5 squared, 5 squared, 5 squared, all multiplied by itself, y times, however many times y is. Yeah, that's what that represents. It's kind of weird. Okay. So how could I get that from the beginning? Like if you recognize that you have 5 to the 2y, you are allowed to write that as 25 to y, right? Because it's 5 squared to the y, right? The only thing I caution against doing this is I taught one of the classes this last, like a couple years ago, and I remember it was Blake Steele. Blake Steele, like, always wanted to use this, and he was really good at it, except when I gave him ones that looked like this, like 3 to the 2 to the x. Because that's not the same thing. You can't say it's 3 squared to the x. You can't be like, oh, that's 9 to the x. Do you understand the difference? It's a slight one, right? If you had 3 to the 2x, you can write that as 3 squared raised to the x, right? But you can't do that for 3 to the 2 to the x. So just be careful with things like that, but always look for the ways that you could simplify and think. Like as you're doing your homework, I've told you this before, like really think about your homework. That's the point of homework. Don't just rush to get it done, and think about ways that they could write that. All right, so let's stop there for now.